Good morning, students. I am Venkatesh Kesi. Welcome back to finite element analysis classes. Module 3, class 2, that is analysis of beams. In previous classes, we have discussed Hermite-shape functions and we also derived Hermite-shape functions, that is h1, h2, h3 and h4. And for these four Hermite-shape functions, considering we have also derived element stiffness matrix, and on deriving we got the element stiffness matrix, that is Ke of 4 by 4 matrix, and that is a element stiffness matrix for a beam element we have derived. And along with this one we also got the equations for load vector due to point loads. And here for a point loads whenever it is acting at midpoint or a midspan of a beam, then the force vector can be considered as F1 M1 F2 M2, where F1 is the force at left node and that can be considered as P by 2, and M1 is the bending moment and that is dependent upon the load P, so we will be considering it as PL by 8. Similarly, at node 2, that is right node, P by 2 and minus PL by 8. And the second load vector condition, considering the UDL, uniformly distributed load, we can consider it as the forcing vector F is equal to F1 M1 F2 M2, where the left node can be considered as P0 L by 2, and because of the UDL we can consider it as P0 L square by 2, P0 L square by 12 at node 1 or left node. Similarly, P0 L by 2 at node 2, that is right side node. Along with that one, the moment M2 can be taken as minus P0 L square by 12. Now, considering this one, remember this table for the solving of the problems. Suppose when we are considering a what you call as a beam, a simply supported beam subjected by a point load P, we can consider it as the forcing at node 1 or node 2 we can consider node 1 P by 2, and the bending moment we can consider as P L by 8. At node 2 or the right side node we can consider it as P by 2 minus P by L. Similarly, when it is subjected, when a beam is subjected by a UDL, we can consider the forcing function as P0 L by 2 and the moment we can consider it as P0 L square by 12. Similarly, at the right node or node 2, we can consider it as P0 L by 2 minus P0 L square by 12. And similarly in the case of UDL and VVL. Just remember this table, and this table is available from your finite element analysis college textbook, and the same thing I have been copied here. And now, considering this table and this equation, we will move to solve the problems. Now let us consider a problem. There is a cantilever beam which is subjected to a uniform load P0, which is shown in figure. Here, solve the displacement, rotation and nodal forces. Assume the beam to have uniform rigidity. Take E into I throughout its length, that is E into I, Young's modulus into we can consider that as E into I. Along with this one, for this one, the steps we can consider it as, now the first step is convert the physical model to finite element model. Now whatever the model he has given, this is a physical model. Now we need to convert this physical model to FE model, and that FE model, which includes only element, that is the element, this is an element, and here you can observe the node 1 and node 2, and at node 1 we can have the displacement as V1 and the moment and the slope because of the moment theta 1, and at node 2 because of the forcing function F2 there is a vertical displacement V2 and angular rotation as theta 2. This is the first step, convert the physical model to finite element model. Second step, that is writing the element stiffness matrix for a beam element. Element stiffness matrix for a beam element can be considered for a single element. Here we can be considered stiffness matrix as K is equal to EI by L cube or LE cube, where L is the length of the element and E is the Young's modulus and I is the polar moment of inertia into 12 6L minus 12 6L 6L 4L square minus 6L 2L square minus 12 6L 12 minus 6L 6L 2L square minus 6L and 4L square. This is your element stiffness matrix for one element. That is step 2. In step 3, we need to, there is a global stiffness matrix. Global stiffness matrix can be written as the summation of K is equal to K1 plus K2 on plus, we can consider, if at all there is a 2 or more elements, we can consider as K1 plus K2 plus K3 and so on. Since in this model we have considered it as a one element, then global can be considered as K1, and along with this one we need to mention the displacement vector and force vector. That is step 4, global nodal displacement vector and load vector. Here global displacement vector we can consider it as Q. Q is equal to V1 theta 1, that is at node 1, and V2 theta 2 at node 2. V1 is a linear displacement and theta is the angular rotation or angular displacement, and V2 is a linear displacement and theta 2 is an angular displacement. Similarly, a load vector we can consider it as F as at node 1 we can take it as P naught L by 2 and F1 because of F1, and M1 we can write it as P naught L square by 12. At node 2 we will write as F2 as P naught L by 2 and M2 as minus P naught L square by 12. Now this is the step 4, that is global nodal displacement vector and load vector. Step 5, that is equilibrium equation. Equilibrium equation we can write it as KQ is equal to F, where K is the global stiffness matrix and Q is a global displacement vector and F is the global force vector. Here K, whatever the K value we have taken, K into Q, that is a K value already we have taken as a global stiffness matrix, and Q is the global displacement vector V1 theta 1, V2 theta 2 and V2 theta 2. And similarly the forcing vector we can take it as F, that is equal to P naught L by 2 minus P into P naught L square by 12 and P naught L by 2 and P naught L by 12. Similarly, step 6, after considering the equilibrium condition, we need to apply the boundary condition. Since we can observe the node 1 is fixed, so node 1 is fixed, V1 is linear displacement, vertically movement displacement is 0, and along with that one the angular displacement or the slope also will be 0 at node 1. Now by using elimination method of boundary condition, we need to eliminate the corresponding row and column with respect to V1 is equal to 0 and theta 2 is equal to 0. That is, since node 1 is fixed, we will consider it as first node, and whatever the corresponding to the first node we will be eliminating corresponding row, that is the first row and first column should be eliminated. And similarly, whenever the node, second node, if I am constraining for the second node, that is if it is restricted for the moment, so eliminate second row and second column. On simplification we will be getting only, that is EI by L cube, that is 12 minus 6LE minus 6LE 4LE square. On simplification, therefore the displacement vector, that is a linear displacement V2 is equal to minus P naught L to the power of 4 divided by 8 EI, and similarly theta 2 is equal to angular displacement, that is P naught L cube by 6 EI. This is the problem, that is where we need to determine the displacements, that is a displacement, linear displacement and angular displacement, that is a rotation. Theta 2 is the angular rotation in radians, and V2 either it may be in terms of meters or centimeters or mm. Now we shall move for the next problem. Here the problem number 2, determine the maximum deflection and the internal loads in the uniform cross section of the cantilever beam shown in the figure if the beam is treated as single finite element. And here in this problem he has given Young's modulus as 70 GPa and polar moment of inertia I as 4 into 10 raised 4 mm to the power of 4. Either, and here the dimensions here for it is a cantilever beam with a point load as well as there is a UDL of 10 kilonewton per meter and a point load at the free end, and total span of the beam is 4 meters. Now the first step is to convert the physical model to FE model, and here in FE model which includes only nodes, that is which includes only nodes, there is node 1 and node 2 and elements, and since it is the length of span is 4 meter, we need to take it as 4 meters. So this is the finite element model. The finite element model should only include the lines as well as the nodes. And step 2, write the element stiffness matrix. Element stiffness matrix for because it is a single element, we will be considering the element stiffness matrix as K is equal to EI by L cube, 12 6L minus 12 6L 6L 4L square 2L 12 12 6L, and here also 6L 2L square minus 6L 4L square. Now considering it as a only one element, we can write the values, we can substitute the values of L, length. Here EI, Young's modulus into moment of inertia I can take it as by L cube, where I can be taken in terms of meters, that is a Newton meter. I will be considering it as 7 into 10 raised 10 Newton per meter square, and along with that one moment of inertia is given as 40 into 10 raised minus 9 meter to the power of 4 divided by L cube. So we will be considering it as 43.75 Newton meter. Total EI by L cube, we can take it as 43.75 Newton meter. Now substituting along with this one, we know the values of 12 6L. Substitute all the values, the interior elemental length L as whatever the length is given, that is a 4 meters. Substitute the value of 4 meters. Now on substituting, we will get the element stiffness matrix, that is 43 EI by L cube is 43.75, and on substituting the value of L, we can get the matrix as 12 24 minus 12 24 24 64 minus 24 32 minus 12 minus 24 12 minus 24 24 32 minus 24 and 64. This is the element stiffness matrix for the beam element. Third step is global stiffness matrix. Global stiffness matrix, we have the total combination of the element stiffness matrix of element 1, element 2 and element 3 and so on. Since it is only one element here, we will be considering the same element as global stiffness matrix, the element stiffness matrix as the global stiffness matrix. This is step 3. Step 4 is a global nodal displacement vector and load vector. We can consider the load vector Q is equal to V1 theta 1 for the node 1, V1 theta 1 as node 1 and V2 theta 2 at node 2. And along with this one, we have the forcing vector F is equal to P0 P naught L by 2, P naught L square by 12, P naught L by 2 minus P naught L square by 12, that is transpose. Now considering this global stiffness matrix, global vector, global nodal displacement vector and forcing vector, we'll go for here the load vector along with the UDL there is a point load. So the UDL, whatever the UDL point load we are considering, that is P naught is minus 10, and since it is a acting downward direction, we will consider P naught as minus 10. Minus 10 into L is 4 divided by 2, and the second one is minus P naught L square by 12, minus 10 into 4 square by 12. And at node 3, at node 2, along with the UDL, we have the vertically downward point load, that is minus 10, minus 100. We need to consider that at node 2, along with this one, we have the moment, that is P naught L square by 12, that also we need to consider. That is, as it is acting downwards, and along with that one minus into minus, we have the positive values. So the load vector will be minus 20 kilonewton at node 1, that is at node 1 minus 20 kilonewton, along with that one minus 33.33 kilonewton meter, that is a moment, and along with this one we have at node 2 minus 120 kilonewton meter, and at node 2 there is 13.33 kilonewton meter. This is the global load vector. Now considering the global stiffness matrix, global load vector, global forcing vector, we write the equilibrium equation as KQ is equal to F, where K is the global stiffness matrix equation and Q is the global displacement vector, and forcing function, already we have taken the values, that forcing function we need to mention. This is step 5. Step 6, we need to apply the boundary condition. Since node 1 is completely fixed, and if it is completely fixed, we will consider it as the linear displacement V is 0, so V1 is equal to 0, and rotation at that node 1 is also 0, that is theta 1 is 0. Using elimination method of boundary condition, take this as theta 1, not theta 2, take this as theta 1, and using the corresponding we need to eliminate the corresponding row of V1 theta 1 and V2 theta 2. So since node 1 is fixed, we will be considering first row and first column. First row and first column should be eliminated. Along with that one, since it is an angular displacement of theta 1 is also 0, that is second row and second column should also be eliminated, and remaining is only these rows: 12 minus 24 minus 24 64, and on simplification we have the, on reduction of the matrix we have 43.75 into 12 minus 24 minus 24 64 V2 theta 2. The unknown displacement vector is V2 and theta 2. Therefore on simplification we get the value as V2 is equal to 0.8762 meter and theta 2 is 0.3238 radians, that is a nodal displacement vector. Therefore the nodal displacement vector, global displacement vector, we can represent it as, at node 1 there is no any displacement, so we will consider it as 0 and 0 since it is fixed. At node 2 we have the linear displacement as, that is V2 as minus 0.876 and the angular rotation as minus 0.3238 radians. This is the second problem where we need to determine the nodal displacement. We shall move for the third problem. Here consider the third problem. A third problem is a simply supported beam which is subjected to a uniformly distributed load. Here obtain the slopes at the support and the maximum displacement in the beam. Take Young's modulus as 200 GPa and polar moment of inertia I as 2 into 10 raised 6 mm to the power of 4. Now look into the sketch here. The total length of the beam is 1 meter, and one end it is completely fixed here, at the left end it is completely fixed, but whereas at right end it is allowed to roll in the x direction. Because of the rollers, there is a tendency of the end, right end, the tendency to have the further x moment. So the UDL is 12 kilonewton per meter. The data which is given here is Young's modulus is 2 into 10 raised 5 Newton per mm square, or we can even reduce to E is equal to 2 into 10 raised 11 Newton per meter square. Since the length is in meter, I will keep all the values in terms of meters. And I also has given as 2 into 10 raised 6 mm square, and we will convert it as 2 into 10 raised minus 6 meter square. Therefore, E into I, the value of E into I is 2 into 10 raised 11 into 2 into 10 raised minus 6, that is 400 kilonewton meter square. This is the data which he has given. Now considering this data, and here the first one is converting, the step one is convert the physical model to FE model, and FE model should include only the elements as well as the nodes. Only the elements as well as the nodes, node 1 and node 2. Here we will consider it as a single element. Now step 2, we will write the element stiffness matrix. Element stiffness matrix for a beam element is given as K is equal to EI by LEQ, that is 12 6L minus 12 6L 6L 4L square minus 6L minus 2L square minus 12 minus 6L 12 6L 6L 2L square minus 6L and 4L square. Since it is only one element, along with this one we need to substitute the values of EI by LEQ. As all the values we have maintained in terms of meters, 200 into 10 raised 9 into 2 into 10 raised minus 6, that we will get it as 400 kilonewton meter, and L is 1 meter and 1 cube will be considered. Step 3, nodal displacement vector. Step 3 is nodal displacement vector, and here since we have only one element which includes, keep node 1 and node 2. Node 1 which is subjected, we can consider it as V1 as a linear displacement, theta 1 as angular displacement, and V2 at node 2 as linear displacement and theta 2 as the angular displacement. Now along with this one we need to have the loading vector, and load is force vector, we can consider it as force vector or load vector. Force vector F is equal to F1 M1 F2 M2, and the load vector, because of UDL, we can consider it as F is equal to P naught L by 2 at node 1, P naught L by 2 as a forcing, and bending moment M1 as P naught L square by 12. Similarly, at node 2, the force is P naught L by 2 and bending moment as minus P naught L square by 12, because the total beam is subjected by an UDL, and this UDL is acting in downward direction. Since the UDL which is acting in downward direction, we will consider the value P naught as minus 12 kilonewton per meter, and the force wing. Now substitute the value of P naught is equal to minus 12 kilonewton per meter here in the loading vector. On substituting, we get the value P naught is minus 12 into length is 1 meter by 2, that is 12 by 2 is 6, that is minus 6, and similarly P naught L square by 2, that is P naught, that is minus 12 L square is the same thing, minus 6 minus 1. Similarly we will be getting at node 2 as minus 6 and 1, and here remember you need to mention V1 theta 1, node 1 V1 theta 2 V1 theta 1, and node 2 on node 2 V2 theta 2. This is step number 4. Step number 5, equilibrium equation. We write the equilibrium equation as KQ is equal to F, where K is the global stiffness matrix and Q is the global displacement vector and F is the forcing vector. Now we will represent in terms of the already we have derived and we got the values of K. K is equal to 400 into 12.6 minus 12.6, 6.4 minus 6, 2, minus 12 minus 6, 12 minus 6, 6, 2 minus 6 and 4. And we need to determine the displacement, that is V1 theta 1, V2 theta 2, and forcing vector as minus 6 minus 1 minus 6 plus 1. This is the equilibrium equation. Now step number 6, apply boundary condition. See, since node 1 is fixed completely, we have the linear displacement V1 is 0 and angular rotation theta 1 is also 0. And along with that one, at node 2, it is provided with a roller. You can look into the sketch there. Along with the beam, that node 2 is provided as a roller and it is restricted to move in downward direction. So we will consider it as V2 is equal to 0. And it is able to, since the roller is tending to move in x direction, there is a possibility of the angular displacement. So we need to have to determine theta 2. So using elimination method of boundary condition, eliminate the corresponding row and column of V1, theta 1 and V2. So we rewrite the equilibrium equation, that is KQ is equal to F again, and by considering this one, since node 1 is fixed and there is no any linear displacement or angular rotation, so corresponding row, first row and first column should be eliminated. And along with this one, there is no any rotation at node 1, so that is theta 1, V1 theta 1, second row and second column should be eliminated. And next, at node 2, V2, there is no any vertical displacement, so V2 is 0. Since V2 is 0, that is a third column and third row should be eliminated. And remaining value is only the angular rotation. That angular rotation we need to determine from this equation. Therefore, the angular rotation theta 2 is 400 into 4 theta 2 is equal to 1 and theta 2 is equal to 0.000625 radians. This is the first bit where we need to determine what is the angular displacement in the model. Since it is a simply supported beam, one it is completely fixed and other end there is a roller. And along with this one, the second bit is we need to determine the maximum displacement. See, in the total length of the span, when it is the either ends, because of the UDL, we get the maximum displacement exactly at the midspan or at the center. To determine this one, we will be considering the Hermite-shape functions. So, to determine the Hermite-shape function, we have the equation V is equal to H into Q, where H is the Hermite-shape function matrix into Q is the global stiffness matrix vector. Here, where V is equal to H1 V1 plus LE by 2 H2 theta 1 plus H3 into V2 H3 into V2 plus LE by 2 into H4 theta 2. So, at midpoint we will be considering it as 0, whatever we will be considering linear displacement. And from boundary conditions we have on the we need to determine what is the maximum displacement at the midpoint. And we have the boundary condition, that is V1 is 0 and theta 1 is also 0. And at node 2 there is no any vertical displacement, so V2 is equal to 0. Substituting these values in the above equation, then Substituting these values in the above equation, we may get the values of the maximum displacement. Therefore, Vmax is equal to Le by 2 into H4 theta 2. So, where we need to consider the value of Hermitshev function H4 as 1 by 4 into 1 minus zeta plus zeta square plus zeta cube into theta 2. So, at midpoint, we need to consider there is a maximum displacement on theta 2. Therefore, the maximum deflection at the midpoint is 7.8125 into 10 raised 5 meters. This is it. By using Hermitshev function, we have solved the problem and we have determined the maximum deflection at the midpoint. In the next sessions, we will be continuing with the Hermitshev functions by considering the other beams which can be loaded by either point loads or UDL. Thank you.